Hey guys, 9-1 inverse variation part 2. This one we are looking at the second objective using joint and other variations. We have just two examples that we're looking at today. Before we look at an example though, let's take a look at this information that the textbook provided for you. There's this nice little table above example 4 in the textbook, and it says it is possible for 3 or more variables to be related. So please don't panic when you see a whole curmudgeon, conglomerate, whatever you want to call it, mishmash of terms. When one quantity varies with respect to 2 or more, the result is a combined variation. For example, a variable z can vary directly with both x and y. You can model such a joint variation with the equation z equals kxy. You have to have the k because that's your constant of variation. And sometimes that can be a little bit tricky because if you just see, for example, z equals xy, you may be tempted to think that it doesn't have a constant of variation when in fact the constant of variation would be 1. So always remember, if there is no explicit constant of variation, then it's usually 1. All right, so now take a look at some of these examples they provided. So the first one we've discussed. Second one, z varies jointly with x and y and inversely with w. So it did go in order. Jointly with x and y, so those are being multiplied. Inversely with w, so that means you're dividing. The w is going to be in the denominator. It's the inverse. Z varies directly with x, and then inversely with the product wy, right? So again, you can see how that plays out there. All right, take a look at example 4. All right, so a lot of times we see in physics predominantly a lot of different formulas that we're using that have direct variations and inverse variations, all right? So it's a combination of. This one says Newton's law of universal gravitation is modeled by the formula F equals capital G m1 m2 divided by d squared. F is the gravitational force between two objects with mass m and m2, and d is the distance between the objects. G is the gravitational constant. So G is your constant of variation. Okay, so one more time. Even though it's G is the gravitational constant. That is your constant of variation. That would be the equivalent of your K in this case. Describe Newton's law as a combined variation. So that's what we're going to be doing here. Is we're taking these equations and we're putting them into phrases. All right, so in the numerator, you have G, M1, M2, but remember G is your gravitational constant. It's not discussed when we are talking about whether it varies directly or inversely. Okay, so F varies jointly with the masses M1 and M2, and then F varies inversely with the square of the distance D. All right, easy peasy. Actually, you don't have to say the F part here in this one, and you wouldn't have to necessarily say distance and masses. So to cut this down to, cut it down to the chase, for lack of better words, F varies jointly with M1 and M2 and varies inversely with the square of D. Okay? All right, so now let's take a look at this one for your notes. Right? The mass M of a moving object is related to its kinetic energy, K, different than the constant of variation. So it's related to its kinetic energy, K, and its velocity, V, by the formula M equals 2K over V squared. Describe the relationship as a combined variation. All right, so here's the tricky part. Okay, so again, and I said it, in this case, K is representing the kinetic energy. It is not the constant of variation. Don't you just love the formulas from physics? Yes. All right, so we have two different things going on here. We see that M is going to vary, right? So if we have M equals 2K over V squared, we see that M varies directly with k. Oh, my handwriting is atrocious. And it varies inversely, and you could even cut out the varies part and just put inversely, and I would be okay with that. Varies inversely with the square of v, as in Victor. All right, now this guy here, this 2, this is your constant of variation. Nice, right? All right, so again, looking at the original equation, the original formula, m equals 2k over v squared. So m is going to vary directly with k and inversely with the square of v, right? Okay, so let's go ahead and take a look at example 5. And I chose this one as opposed to the one that was actually suggested by the textbook author because I think this one lines more closely with what you'll be doing in the homework as opposed to the one that would be your textbook author suggestion. All right, so here we go. Suppose z varies directly as x and inversely as the square of y. So it's varying directly as x, and it varies inversely as the square of y. When x equals 35 and y equals 7, the value of z is 50. Write the function that models a relationship and find z when x equals 5 and y equals 10. Okay, so there's a lot going on there. The very first thing we want to do is take a look at this first sentence. And we want to write an equation given those variables. All right, so we know that z is going to vary directly as x and inversely as the square of y. But what do we know that all direct inverse variations and direct variations have? Now, just to kind of refresh, take a look over here. If it varies jointly with x and y, we have a k. If it varies directly with x and inversely with the product wy, we have kx in the numerator, wy in the denominator. So that means we have to have that constant of variation. And in this case, we are going to use k because that is our variable that represents that in Algebra 2. Okay, so this is the formula we have. Z equals kx divided by y squared. All right, so first sentence, done. Now, the second one, when x equals 35 and y equals 7, the value of z is 50. Okay, so we're going to take this equation we just created and substitute in the 3 values that were given. We have z is 50. We know that, we don't know k yet, x is 35. And we know that y is 7, and that is 7 squared according to this formula. So now we have 50 equals 35k over 49. We need to solve this for k. So I am going to start by multiplying both sides by 49. And honestly, I don't know what that is off the top of my head. And I should because it's pretty doggone easy. Not 2,500, 2,450 maybe, I'm thinking, but I'm doubting myself and it's better to double check. So 2,450 it is. Okay, so we have 2,450 equals 35k. And now we need to divide both sides by 35. And I'm going to use that handy dandy calculator over there because it's going to help speed things up and then I don't have to look stupid. All right, so there's 70. Okay, so 70 equals k. And that's our constant of variation. Now we're going to take this and we're actually going to put it back into that original equation. Okay, so then we have z equals 70x over y squared. That is the function that models this particular section or this particular situation given this information. So now it says write the function that models the relationship. Done, we got that. Woohoo! And then find z when x is 5 and y is 10. All right, we can do that. So we need to find z when x is 5 and y is 10. Okay, so in the numerator, we would have 350, right? And then in the denominator, we would have 10 squared, which is 100. 350 divided by 100 is going to give you 3.5. All right, so those are the two answers that we have. We have our function, and then we have z when x is 5 and y is 10. And that's all she wrote. So again, hopefully you find this pretty easy. It does have steps, but at the same time, after a chapter of logs, hopefully you find this a little bit more algebraically friendly. So if you have any questions, just let me know.